it's my pleasure to welcome Horng-Tzer Yau, who will talk about random metric statistics, a new class of statistical laws for highly correlated systems.
Thanks a lot for the invitation. I'm sorry I didn't notice that the title is slightly different, but anyway, so especially it's I mean, whatever it is, the content is what I want to say, and the title is slightly wrong. Sorry. So this is a joint work with a lot of students, postdoctors, and collaborators, and so on. And some, I think, many of them are already. There are many of them already professors, and so I will not go through all the names, and let me go down to the talk. And so I want to start. I assume that you have never heard this talk. So then I'll just start from talking about introducing the history. And this stuff it's really stuff on the in the 1960 or maybe late 1950, is by Eugene Wigner. And he, at the time, he was trying to understand the nuclei structure, or the resonance of nuclei structure. Then, I mean, you can imagine that how difficult was the problem, because the nuclei has so many particles, and you want to predict their spectrum, and then it's many body quantum mechanics problems, and the interaction of nuclear force is not completely obvious. And so we're gonna come up with an idea. His idea is he want to use random matrices to model the behavior of a many body quantum system. So he comes up with the idea. He said that the successful energy levels of a large nuclei, he believed the behavior is universal. And then it's not just that, it can be described by the spectral statistics of random matrices. So this is his key idea. And it's quite dramatic, and in a way that, first of all, I don't know why he came up with random matrices. And the history I knew was he started to use the random Schrodinger equation, but he couldn't solve it, and he started to make these random matrix models. So now let me start to describe what's the random matrix. And so random matrix, you take a matrix with let's say it's a symmetric, it's a real number, and you can also consider the complex or quaternion and so on. So there's different class. But let's just stay with the real case. And now then you assume each metric element, besides they are symmetric, they are normal distributions with mean 0 and variance 1 over n. So here is a graph of normal distributions with variance 1. And now here I use the variance 1 over n, because this is a normalization instead of 1, because I want the eigenvalue to be order 1. So this is normalization. This is not important. And now I start to order the eigenvalues, and with this normalization, the eigenvalue is order 1. Now this is called the Gaussian orthogonal ensembles, and then now this H, instead of called the Gaussian orthogonal ensemble, is we'll call this Wigner ensembles if the metric element Hij are just independent but not necessarily normal. Then it's called a Wigner ensemble, Wigner matrices. All right. Now Wigner proved a Wigner semicircle law. He said the eigenvalue density. The eigenvalue density is given by the semicircle law. So you can see that this is semicircle law, and this is eigenvalue density. But you see the density is actually very crude, because the density only tell you that if you take an interval, if you take a small interval size, take an interval size epsilon, and then you can ask how many eigenvalues inside. But on the other hand, when physicists study the the resonance of the scattering, what they want to know is a gap, is a distance between the eigenvalues. So what we're gonna say is really the probability distribution of the eigenvalues of the difference of the eigenvalues. It's actually the difference of two eigenvalues. Then this has a universal law. That's what he claimed. What he claimed is that if you take a random matrices and now you look at the probability law of the difference of of the eigenvalues, then this law is the same as the many-body quantum mechanics. So this is quite I mean, as it is, nobody can prove anything like this. It's actually a question much easier. It's still completely open. Even if you take a Laplace operator with a random potential, then this is one body problem. So this problem is still completely open. So over time, there's an easier question, which is now this. Suppose we are not ambitious. We want to study, this quantum many-body system and so on, or even just random Schrodinger equations. Now let's just take a matrix, and now we ask that whether this probability law of the eigenvalue of successive eigenvalues, this probability law, whether this probability law depending on the probability distributions of the metric element. So the question you ask is whether this law is independent of the metric, the probability distribution of metric element, and this is really the question you're asking. So you're asking the successive eigenvalue distribution, whether it's independent of the probability distribution of the matrix. Now, I have to add that in the case of this Gaussian case, one can all this quantity has an explicit expression in terms of spatial functions. And people calculate a lot of that, and those are, those are lectured by itself, and there are a lot of spatial function calculations, and this one to compute this one for the Gaussian case. And then it's not just that; you can also do the edge distribution, because you see the eigenvalue are near the edges between -2 and 2. You can also ask the probability distribution near the edge. And this is a whole different class of questions and so on. But let's just stay for now. Let's just stay in the interior. And now you ask the question whether this is correct. It's independent probability law of the matrix element. And this is called the Wigner-Dyson meta conjecture. And of course, I mean, Wigner, Dyson, and Meta, they never really made this conjecture themselves. And but this conjecture was stated explicitly in the Meta's book. If you read Meta's book on random matrices, and in the introduction, he already mentioned this question, whether this question is correct or not. So now, we have a situation quite close to the classical central limit theorem, because the classical central limit theorem says if you take a random variable, you can normalize it, then you become Gaussian. And even though each individual metric element is not Gaussian, but still, if you take an average, then you become Gaussian independent of your metric law. And so in this sense, so this is an extension of the classical central limit theorem. Now, so the the truly ambitious vision is the following. It says if you take a system you take a highly correlated system, it's simply because their correlation is everybody interacting with everybody else. So this means the random matrix statistics is actually a good model for these highly correlated systems. So in a way, he was trying to create a class of probability laws, which is on the other end of the independent of the Gaussian distribution, because Gaussian is for the independent case, and here he want to construct something for the highly correlated case. So it's extremely significant because you thought that when system has a correlation, it becomes so difficult to study. But what we're going to say is if the correlation are really high, really large, then actually you can study the problems. And the random matrix actually give you the law. But whether you can prove it is a different story, but his vision is this is correct. And it's a good model. Now, this weakness idea is not without people objected. For example, now, so here this George Uhlenberg, he asks a simple question. He says, now if you take a Wigner ensemble, then it's always semicircle law, right? And now, if you take any other physical system, then they will not have a semicircle law. And now, so if the prediction of the random matrix model, even for the density is incorrect, how can you expect that other prediction of random matrix theory? So it's quite a rational objection. But actually, what's interesting is actually that the density is the one which is incorrect. But if you start to ask the local statistic, then it's become correct. So it's quite funny that random matrix did not give you the leading order behavior, but the local correct. Now is the belief. So now, so this is so-called the Wigner-Dyson meta conjecture, and it was proved in many cases in the last 10 to 15 years. And the original case of about Wigner ensembles. So this was so we start to look at this problem in about 2008 and 2009, and it took about 6-7 years to get the strongest form. And the strongest form is if you assume the metric element has 4 + epsilon elements, moments finite. The metric element's moment has to be finite up to 4 + epsilon moments. Then this conjecture is correct. And in the beginning, the Tao and Wu had some partial result, but in this in the complete general form, this was a few years ago's result. And now this was a student of mine, and he extended this 4 + epsilon to 2 + epsilon. And then I will also explain to you, actually, you can even go beyond this in a second. Okay. Now the other question is now this is just about Wigner matrices. And you want to extend your class of problem not just to Wigner matrix. You want to go to many different things. And for example, there's a huge class of problems about the adjacency matrices of random graphs. And for these problems, it's called the Ergodicity graph or deregular graphs. And there are many works. And I would talk about some of this if I have time, and so I'll mention some of this. And the other one is you can also, the metric element can also have a correlations, and this Erdős, he did a lot of this. And the last one I want to mention is there's something the most ambitious one is the non-mean field models. So if you think about the random if you think about Schrödinger equation, the Schrödinger equation is called the non-mean field model because the physics law tend to be local in the sense that the particle only interact with its neighbors. It's not everybody interact with everybody else. It's really interaction is quite local. So quite local, then so if you think about the matrix, so now let me go back to the matrix. So this matrix is sort of considered as mean field because you see the metric elements is appear everywhere. But on the other hand, if you look at the random Schrödinger equations, if you knew about this subject, then the metric element has some diagonal terms and a few off diagonal terms, and most of them are zeros. So this is called a non-mean field model. So non-mean field model is really very difficult, and so there are some partial results for the band matrices, and but probably I don't have time to talk much about this. Okay. Now about these 2 plus epsilon moments and so on. So there is a class of problem. Now it's called suppose you want to assume that your probability law does not even have a second moment, for example. So you start to consider a probability law has a fat distribution, has fat tail. So this kind of fat tail. The fat tail probability distribution, the most common one is called this alpha stable law. The alpha stable law is characterized by the characteristic functions is given by this form. There's a t to the alpha here. And this is equivalent to the probability of x bigger than some constant k is k to the minus alpha. So you can see the alpha between 0 and 2. If alpha is bigger than 2, then you start to have a second moment. And alpha between 0 and 2 is, roughly speaking, alpha is how many moments you can have for these random variables. And so in the joint work I have with Agawa and Pato, we actually go to something below the second moment. And so the theorem is stated the following. The theorem. So now the statement theorem here in English is quite a bit complicated. If you want to read it, it's sort of very long. And but let me show you in the graph. Okay. So in the graph is the following. In the graph is now this alpha here. This point is alpha equal to 2. So between alpha equal to 1 and equal to 2 is this so-called this Wigner-Dyson meta conjecture is hold between 1 and 2. So this means the transition point for the, if you look about the moments, it actually can go below 2. It actually go up to 1. And now once it go below 1, it's even more interesting. Go below 1, then there's actually a curve. It's believed that there's a curve, and so on this side of curve, it's this is correct. On the other side, it's called on the other side of curve. Then you only have the on the other side of curve is the so-called localized regions, and the eigenvalue statistic becomes the Poisson. But anyway, but none of this was proved, and so our result says we can find the curve here, and so inside this curve is this random matrix statistic is still correct, and on the other hand, outside then we don't know. And this was resolved by physicists, and they have actually two different conjectures, and I mean they actually conjecture about 2 different behavior, but it turned out that the one in 2016 was correct. I mean our result is consistent with the one in 2016. Okay. And there are some mathematical results and by different, but it's in the completely different regions, and so. And now here I also mentioned this eigenvector. So in these green regions, the eigenvector has some sort of delocalizations. So I would explain this delocalization of eigenvector in later on, because I haven't talked about eigenvector, and so even though their statement here, it's we should just forget about this eigenvector statement.
So it's a little difficult to follow it. Maybe you can tell a little bit more precisely what is localized and what is delocalized.
Oh, I see. All right. Okay. So now maybe then allow me to move my slide. Then I would explain to you what's localized, what's delocalized. Because okay. So look at this sentence here. So if you look at the eigenvector, okay, so you take an eigenvector. The eigenvector has an n component because your matrix size is n. Now this is L2 normalized eigenvector. If the eigenvector are, each component has about the same size, this is called delocalized. So delocalized just says the eigenvector, each component, the size is n⁻⁻⁴. And now you allow some sort of small, small errors, but roughly speaking, it's basically the eigenvector are completely flat. So this is called completely delocalizations. Now localized is completely different. Localized just means they are some, maybe they are entry epsilon coordinates, which all the eigenvectors are mostly inside there, and outside are essentially 0. That's called the delocalized. And this is a two this is a two scenario of the eigenvector behavior. One is the eigenvector are essentially completely flat. The other one is eigenvector are localized in the small regions. And everything we are talking about, you will see that in random matrix, the eigenvector are always completely delocalized. So this I will talk about in the second half of this lecture. Okay. But for now, it's about the eigenvalues. So for the eigenvalues, then you find that for eigenvalue, then what the theorem says, the eigenvalue, local statistical eigenvalues, it's actually the same as random matrix. Even if you don't have a second moment, you can go down to the first, basically go down to the first moment. All right. Now, the next question I would like to address is what about the proof? Okay. Now the proof. So if you look at random matrix history, then you find that in the beginning, when Dyson and the Mehta and Golden, they study this subject, they always study the Gaussian case, and this is because Gaussian case you can do exact calculations, and it was already it's actually not an easy task to even compute the Gaussian case. And now then all the way up to so in the 70s and the 80s, there actually is not much progress of random matrix in mathematical theory. And then once you go to the 1990, people start to study the so-called using this Riemann-Hilbert problem to study the random matrix ensemble. And so there are lots of activity in 1990s, but those technique you cannot study any problem like metric element. So because we take those kind of technique, you cannot study this kind of question that the random matrix elements are independent random variables, because they sort of the probability law do not have enough symmetry to use this kind of method. So so one need a completely different type of method, and this is the method we find that is more suitable for the random matrix universality type questions. And then it's because you want to study the eigenvalue behaviors inside the spectrum. It's not at the edge of spectrum. By the way, I forgot to say, maybe I should say that the so-called this Wigner semicircle law. The Wigner semicircle law was proved by a moment method. So the moment method is you take a metric element, you take a random matrix, and then you go to a case power of these metrics and compute a trace. You take expectation. So roughly speaking, you take expectation of trace h to the k, and then you try to compute as much k as possible, and as high as possible. Then you try to get a result from here. But the troubles of this kind of method is you can see that if you take a trace of a metric to a high moments, then you always get the information at the edge and not in the interior. So there's a trouble of getting information in the interior of a matrix. So the method we are using is the following. It's
did Wigner himself have some heuristic for this semicircle law?
I mean Wigner?
Wigner,
yes. Oh, what Wigner did was he computed expectation of trace h to the k, and he find this one. He find the answer of this. This is equal to the semicircle law computed trace k. See, if you use a semicircle law, the semicircle law is a d mu semicircle of x, and then if you compute the x to the k, then they are the same. So what we're gonna do is essentially something like that, and then you check this for all k finite, independent of n, and then you can see that this one is not difficult to compute because you see the metric element is Gaussian, so the h to the k is just a product of Gaussian random variables. And then you start to calculate everything, so it's pretty computable. And now, on the other hand, you will see that now this will tell you nothing for the eigenvalue inside, and especially if you want to say if you want to ask the question now, if you're asking the question that if you take this eigenvalue inside, and then you even ask the question of this gap. The size of the gap is 1 over n, because you have n eigenvalues. So the size of the gap in the interior is so small, then this kind of method is completely impossible to reach there. So you need a completely new idea, and for a long time there was no idea, and essentially there was no partial result in this province for about 50 years. All right, so the method we are using is, the first thing is we study the green functions. So green function, I will define the green function. I would say once again later on, but so green function is a metric of h minus z. H is your random matrix, and so this is the green function, h minus z. And then you look at component. So you look at diagonal component, but actually you can also look at off-diagonal component. And now if you have eigenvalue lambda j, and uj is the eigenvector, so the A element is uj of A, absolute value square, times lambda j minus E minus I eta. So now this z is a complex variables. So I take z is E plus I eta. Now I don't want to take this completely real, because if it's completely real, then the lambda j, once lambda j equal to E, there's a delta function, and it's pretty bad. So one regularize a little bit with a complex component like that. So this is the and then you can see that if you take the trace of the green functions divided by 1 over n, then it's then it's called this is the Stadial transform of the probability of the okay, never mind the Stadial transform. It's just some names. So if you compute it, is 1 over n lambda j minus E minus I eta inverse. Okay, so this give you so you can see that if eta is quite small, then the main contribution of this summation is coming from lambda j very close to E. And so you can study the eigenvalue very, very close to a fixed energy E if you can let eta very small. And once the eta is go to n to the minus 1, then you basically just have a few eigenvalues, which is the main contribution of this n of z. So the key is you want to study these green functions with these eta regularizations, and the eta has to be size n to the minus 1 plus epsilon. And then you were asking me that why didn't I go to below n minus 1? Because once I go below n minus 1, then you start to see each individual eigenvalues, and then which are fluctuating, and it's very difficult to study. So the green function has a reasonable behavior up to n minus 1 plus epsilon, But once you go below, once you close to n-1, they start to be very, very singular and fluctuating. Now, this is the first step to get some a priori estimate, and this is called a local loss. And the reason you call local is because this eta is quite small. And now, the second step is this is really the the key new ingredient, new idea in this game is you study the dynamics of the random matrix. So suppose you have the initial data called initial value A, and then you take a Gaussian orthogonal ensembles and the time square root t. It's actually not exactly like this. It's really a Brownian motion. I just write a Brownian motion in this funny way, and I mean it's actually incorrect, but I will give a more precise definition later on. So what one study is if you start from a matrix and then you start to let the matrix element to undergo Brownian motions, then this is called then you have a matrix. The probability law is initial data plus square root t plus GOE, and then what you want to do is you want to study what's the eigenvalue, how the eigenvalue change under the dynamics. So eigenvalue change under the dynamics, you start from time 0, and then you keep on going. And then you can see that as time goes become bigger and bigger, then the initial data, the effect of initial data will disappear, and then you will go to the Gaussian. And the Gaussian, this is the answer you wish. But then the question you want to study is at time equals 0, because time equals 0 is initial data. So this is a kind of, it's a very strange, how should I say? Because typically when you study the ergodic, you study a dynamical problem, you want to study the question time goes to infinity. But this is the opposite. You want to study the question time equals 0 by, and then you find this is quite strange because how can a dynamical idea is useful to study time goes to infinity, and while you are interested in the time equals 0. So the idea is the following. The idea is in any dynamical questions. So we first look at the question in the following way. We first say the probability distribution of eigenvalues under small perturbation did not change very much. So you can show that this red period, the eigenvalue will not change too much. On the other hand, there's a separate theorem tell you that once the time is big enough, then you already reach the equilibrium. And then this is blue regions. So in the blue regions, we say that once the time is much bigger than n-1, then the local statistics at this time and at the infinity, they are the same. Now, a separate result says the eigenvalue probability distribution are stable from time 0 to something slightly bigger than n to the minus 1. And as long as this red and this blue has an overlap, then I know the probability law from time 0 is the same up to here, and from here is the same up to infinity. So that's the idea. And it's something quite funny that you try to study a problem by looking at dynamics, but not because the dynamic at time goes to infinity approach to your problem is the opposite. Is the time at infinity, you know exactly this is what you want, but you want to study the time equals 0. Okay. Now, so let me give you examples because I don't want to do too much technical things, so I just stay with something simple and to explain some of these main ideas. Now what we are redoing, I just repeat what I say here. You see the green function is this one I said previously, and now you can see that if I take a trace of g of z, and now if I just take imaginary part, so if I take imaginary part because this is minus I eta, so imaginary part will give me lambda I minus e plus eta square of eta 1 over n. So you can see that the eta just means how precise we talk about our spectral resolution is resolution of how I want to see about the eigenvalues. So you can see as my E go change, and then if once you go close to eigenvalues, though, then you start to see a peak here. So this eta is really how precise I want to do. And actually, our eta is actually bigger than the typical eigenvalue spacing. So if your eta start to become bigger than eigenvalue spacing, then you start to see the density start to look like that. And so then this is now in this case, then this is our eta. So our eta is like this. Then you will not see all this each individual eigenvalues so precisely, but you will be able to see a window of this size n to the minus 1 plus epsilon. But on the other hand, if you put eta very, very small, you can see, you start to see each individual eigenvalues. So this is about the green functions idea. And now about the second step about this, we want to do the Brownian motion of the metric element. It's actually like this. It's really, you look at the stochastic differential equation. The stochastic differential is quite easy. It's you just take a metric element. So each metric element is just standard Brownian motions with your initial data. But on the other hand, it has to be symmetric because we want to stay in the symmetric class. And now here I divide by 1 over square root n. This is the it's just a scaling. So never mind this 1 over square root. Now, so I give you a simple examples of how to do this to prove the central limit theorem this way. So to illustrate the ideas, now suppose I want to prove central limit theorem, which is a theorem everybody knows how to prove it. But now I want to do this by using a dynamical idea. So how do I do it? Now you consider something called Ornstein-Uhlenbeck process. Ornstein-Uhlenbeck process has SDE like the dxi of t. And this is Brownian motions, minus 1/2 xi dt. So for those of you who never seen this before, and don't worry too much with the exact calculations. And this is the process which leave the Gaussian random variable invariant using the Gaussian distribution invariant. Normal distribution are invariant under this dynamics, and this one is called the Ornstein-Uhlenbeck process. Okay, and now we want to prove the central limit theorem. So central limit theorem says the probability distribution of x1 plus xn divided by square root of n as n goes to infinity will become Gaussian. So now I take a test functions f, I compute the x1 of t plus xn of t divided by square root of n. I take expectation and then I take a derivative. So I want to study how the probability law of x1 of t plus xn of t divided by square root of n change. So I take differentiation. So I differentiate this one. Now, because it's already December, close to Christmas, so we don't do calculation on blackboard. And so this is some calculation of Ornstein-Uhlenbeck process you can compute. It's very, very simple. So then you get this line. You do a few lines of calculation. You find that the derivative. You find a derivative of the of probability distribution of time dependent with respect to t. Actually, it has the order n to the minus 1/2 plus epsilon. This order is quite small. So this tells you that their probability distribution do not change up to time t. If time is n to the 1/2 minus epsilon, then this tells you that their probability distribution does not change very much. So this tells you that from time to 0 to time, so the time the n to the minus n to the 1/2, n to 1/2 plus epsilon minus epsilon. So the probability distributions do not change too much. So the probability distribution here and here, they are about the same. On the other hand, we know the so-called Ornstein-Uhlenbeck process, the ergodicity, the time scale is 1. the time scale of Horng-Tzer Yau process, this is 1. So you know that once the time is slightly bigger than 1, say here n to epsilon, here you already reach Gaussian quite strongly. And so in other words, you know from time n to epsilon to infinity, these are the same. About these three are the same. And so then this tells you the proof of central limit theorem. So this explanation is the idea of proving a universality. Actually, you can reduce to 2 ideas. One is in the beginning, there has to be a stability. So allow me to move a little bit here. So you want to have a region, this region, oh, sorry. So these red regions is stability regions. And these blue regions is ergodicity. So if you can establish these 2 properties and then there's overlap, then you're in good shape. So that's the idea. Okay. All right, but now how do we really do it? So if you want to study the metric Brownian motion, so this is the metric Brownian motion. You want to study these dynamics. Now, these metric Brownian motions, it's by itself. If you look at it like this, if you look at each individual component, of course, it's trivial. But the key is that you want to study its eigenvalue behavior and eigenvector behavior. So the eigenvalue behavior and the eigenvector at time t, then you can come, they satisfy SDE. So the first one is eigenvalues will follow dynamics. People call it Dyson-Brownian motions. So this was one of Dyson's most important work, in my opinion. Dyson find that if you take a Brownian motion in the metric element, then the eigenvalues satisfy equation independent of eigenvector. So this equation is independent of eigenvector. I mean, in principle, the eigenvalue and eigenvector equation can couple, but Dyson find that the eigenvalue has an equation by itself, has nothing to do with eigenvector. So this is a very important property. So this eigenvalue equation is called a Dyson-Brownian motion. And then for the eigenvector, if you look at eigenvector, you find the eigenvector satisfy equation, which is much more complicated. This one is the eigenvector has an equation. This is much more complicated. You can see that it depends on the eigenvector equation depend on eigenvector. You see that UL here, and then these are independent Brownian motions, and then it also depends on eigenvalue. So this equation is much harder to study. And I also want to say that on the Dyson-Brownian motion, so now the question is, how do we study this equation? Now, I want to add that the Dyson-Brownian motion, the Dyson write down this equation in 1960. I forgot exactly which year, in the 1960. So let's go to the next page. Yeah, okay, let me stay. The Dyson write down this equation in 1960, but there's the equation do not have any serious estimate about this equation until we look at the problem in about 2008, and in between there are not much progress about to study this equation, and the reason is because this one. If you look at this equation, this is very singular. You can see that this is singular, and why do I say this is singular? Because you see the eigenvalues behavior, the eigenvalue distance is 1 over n. So if the eigenvalue distance can become 1 over n, so this term can become very large. And then you even worry if they are getting even closer, then this equation will become very singular. So it's clear the equation has the singularities once the eigenvalue close to each other. And all the the other thing difficult to study this equation is this is a system of n equations and with a very singular drift. So anyway, Dyson in 1962 he made I mean, it's not exactly a conjecture. Dyson just say in his paper, he mentioned the following. He said that the time to local equilibrium, this is quite strange. The time to local equilibrium for this dynamics, I mean, he didn't call it Dyson-Brownian motion, but this is what we call it. Everybody calls it later on. The time to local equilibrium for Dyson-Brownian motion is n to the minus 1. This is quite remarkable because it says if you wait for time very, very small, then your eigenvalue distribution will immediately become equilibrium. This is quite strange because typically when you study a dynamical question, you expect that you need a long time to reach equilibrium. So how can this be reach equilibrium so fast? And the reason is because it's quite funny. It's because this drift term is so singular. So the drift term is so singular, then this drift term actually will drive the system to equilibrium so fast. And so the rate is exactly this 1 over n is actually exactly the rate. Now, but when Dyson just make this argument, he was just talking about, he basically just, roughly speaking, what he was saying was the distance of two eigenvalues 1 over n, and now you have a classical mechanics of with 1 over n, but then on the other hand, you take 1 over your drift is the inverse of this 1 over n, so the drift becomes large. And now once drift becomes large, so it looks like the time 1 over n is already reached equilibrium. But this statement is difficult to make it's hard to make this into a mathematical statement because you need the eigenvalues. Suppose you can see that if the eigenvalues start to look like this, and then if there's an empty space, then it will take a long time. So, but this one, we eventually give the optimal version to prove this Dyson's conjecture, and this was done with the last results with a student of mine, Benjamin London, and also with my postdoc and some earlier work with Erdős Schlein and so. And at the end, what we say is this Dyson's conjecture is exactly correct, and the assumption you need is for the initial data to satisfy some condition, and this condition was given by the trace of green functions are bounded in. So if you want to reach equilibrium at time t, roughly speaking, you need this empty space. I mean, you need this. If you want to reach equilibrium at time t, then you need the density inside this interval has to be order 1. That's roughly the idea, and then the precise statement is using the trace of green functions to really quantify how fast it approaches equilibrium. And this was this paper is about 2-3 years ago, and so once one proved this Dyson conjecture correct and in such a strong form, then we establish. So let me come back. So this established this part. So this part is Dyson's conjecture. It's proof of Dyson's conjecture. It's proof. Dyson's conjecture. So once you prove Dyson's conjecture, then you establish this Ergodicity part, and then the only thing you need is the initial layer. But I will not talk this more because this is something actually much easier, and also the idea is not as interesting as this part. So I will not do this here. Anyway, so. Now the mathematical statement is a different story. So I hope they give you some sort of idea about what's going on. So now let me spend a few minutes to talk about eigenvector, And I don't think I have time to go to this deregular graph and so on. But let me just talk about the eigenvector. So now eigenvector is called delocalized. The eigenvector delocalized if it's sort of almost flat. Now the delocalization is a basic question in random Schrodinger equation. But then there's also a concept called the quantum unit ergodicity. This quantum unit ergodicity was stated by Rudnick and Sarnak. And the idea is you want to say the eigenvectors on this, you take any negative curve, the compact Riemannian manifold, then the eigenvector will become completely flat, and as the j goes to infinity. So the high frequency eigenvector eventually become completely flat. And this one, this is a refinement of something called a quantum ergodicity. Quantum ergodicity is you are not talking about just one eigenvector. You take some average, and they call quantum ergodicity. Then this is much easier. It turned out that the change from the averaging the eigenvector for a range of energy is much easier, but the single one is really hard. So there are not many examples this can be done, and so this is called a QEE. Now, so for the eigenvector, there are two questions you want to ask. One question is delocalizations. So this is question one. And the second question is about this kind of quantity called a QUE. Now we are talking about a probability case. So if you look at the Gaussian orthogonal ensembles, then all the eigenvectors are given by the orthogonal group ON. So group enough, then you see that this quantum unit ergodicity actually holds with high probability. So this actually is correct for the ON group and with high probability. But now the question is, can you say something like this is correct if the metric element is not Gaussian but just IID? So our question is whether this delocalization and whether this quantum unit ergodicity is correct for the Wegener matrices. And because once you go to Wegener, you don't have a symmetry, and the eigenvector is not exactly ON, but you want to say that it's not exactly ON, but it still look like ON. The theorem we have is actually this is actually correct. And now, because I only have a few minutes left, it's not a good idea to state the theorem and so on. It's so what it roughly speaking is this so-called this quantum unit ergodicity is actually correct in the case of this random matrix settings without requiring the Gaussian distributions. And then the idea, I will not give too much about the idea. The idea to study this quantum unit ergodicity is actually to study this equation. This equation, it's quite difficult to study because you can see the singularity here is lambda k minus lambda L, but here it becomes square, so it's even more singular. So this eigenvector equation is quite singular to study, but on the other hand, this is something can be done, and by studying this equation, we prove this Gaussian, we prove this quantum unit ergodicity for the random matrix. Okay. So I probably should summarize, and so now they are deregular graphs, so let's forget about this, and this expanding graph. So so roughly speaking, the summary of what we are doing is the following. So we prove that the universality of eigenvalues and the QUE or eigenvector distributions, these are all consequences of local ergodicities of metric Brownian motions. You take a metric Brownian motions, you look at eigenvalues and eigenvector, how its evolution, and if you can study the ergodicity very well, then you solve the problem. So the essence of this lecture is if you can study this metric Brownian motion and you can study the flow of eigenvariant and eigenvector, then you can solve the problem. Okay. So the key is really to study the eigenvalue and the eigenvectors evolutions, and this is the Dyson-Brownian motion, or this so-called stochastic eigenvector flow. And now our theory is a local theory, because everything we are talking about, it's not depending on the eigenvalue density over the large scale. It's everything happening in the local scale, so that's why everything. So that's why it's correct. And I didn't say much about the green functions, but in all this study, we need some a priori estimate on the green functions, and this I can't say much today. It's because this was, first of all, it's completely different method, and and the other thing is I didn't say anything about the edge universality, and also this deregular graph, which this topic I didn't really talk about today. And one more thing is, if you want to go to these non-mean field models, non-mean field case, then this is a major question. And so if you look back when this George Uhlenbeck, his objection says if the Wigner ensemble give the wrong answer for the label density, then why do you believe it give the correct answer in random matrix theory in other prediction? Now you can also rephrase, you can paraphrase his question. Now, if you admit the Wigner ensemble is a mean field model, so why do you believe that it models non-mean field systems? I mean, this is quite a serious question. This random matrix is complete mean field model, so why do you believe that the non-mean field is correct? And this is, I think, this question right now it's the most difficult question in random matrix theory. It's not so much that about the random matrix itself. You are asking this question. You're asking them why this mean field model can model this non-mean field behavior, and there are partial results on various questions related to band matrices and Anderson models. But this I will not say much today, and so we end up here. So thanks a lot. Thank you.
Thank you. Do we have any questions?
So when we hear about universality of something, we tend to believe that there is some renorm group mechanism behind this universality. You didn't mention any renorm group here. Is there anything?
You are asking the normalization group? Is that what you're asking? Yeah. No, this there's no, as far as I know, there's no normalization group picture of this question. It's you see the whole, I think up to 2000, maybe 2006 and 2007, everything was either the model has to be invariant models, and then you just study especially computable models, and then the other question is then once it's not computable, then what do you do with it? And the Dyson's idea, Dyson using this look at this question of the Dyson-Brownian motions. So Dyson's original motivation was just to find the dynamics which leave the Gaussian, this GOE, Gaussian orthogonal ensemble invariant. And so he was trying to find the dynamics to leave the Gaussian invariant, but it's not really. He was thinking about how to use this to prove it, to give a picture of universality, and there's no other intuitions that one can have to establish universalities, and so right now this the other idea, or actually the idea one also used quite a bit, is so-called Lindeberg idea of replacing metric element by Gaussian one by one. But no matter what, there's just no renormalization group I picture how this is correct. I mean, you can also ask a similar question: is there this RG method for the central limit theorem, and which is still not quite there.
The central limit theorem can be so presented in that way. It's in the Blecher and Sinai has some exposition.
Yes, yes. It's I mean, you can start to say, you can start to divide this this n probability law to half and half and so on. But I don't know how this kind of picture can be implemented in a random matrix setting. There's I think up to now there's nobody give any other explanation why this universality holds, to my knowledge.
Okay, thanks.
Yeah, thanks for the question.
I have a question. Can you comment on this fact that I've heard, but I don't know about it in detail at all, that there is a maybe strong numerical evidence that the zeros of the Riemann zeta function are related to sort of two kinds of matrix models. Here's a story I remember. First, there was an approximate picture, and then further calculations deviated from it, and then the model was changed slightly, and then it fit perfectly. But these are all things I've heard superficially. Can you comment on how it might be related? Matrix model, zeros of the zeta function.
Oh yes, this is the whole industry. Actually, it's what people find out is the zeta function zeros and this level spacing has the same probability distributions if you look at the zeta function. And but for the zeta functions, if you take analytic functions with a complex support, and the support has had very rigid conditions, it's actually a theorem by Montgomery. And this
assumption. What is the assumption?
Well, you take sorry. It's what you want to do is you want to compute lambda I minus lambda j, and you're asking that whether this kind of quantity and using test function summation over ij. I forgot. I can't really write down exactly what it is, but it's something look like that. So this is talking about the zeros of zeta functions, and if you take a f is analytic, and then you look at quantity like this, then one can really show that it's the same as eigenvalue calculations, but with the GUE, with the it's not Gaussian orthogonal. This has to be complex. This metric element is complex, and then if you look at the law of the complex random matrices, then their probability law and the zeta probability law, the zero of zeta function are believed to be quite similar. And this is not, but on the other hand, they lots of this was not theorem, and then some of the results are under the assumption that the zeta zero is on the critical line. One can actually show many of them actually can be proved. But it's not. There are many things. It's not just the spacing. There are many other properties are quite similar to each other. But especially one believes that if you just look at the gap distribution, now that it's the belief now that they are actually the same as the Gaussian unitary ensemble. But
you have an
but there is no explanation why this is correct.
Oh, okay. Did you have it? I was asking, do you have any idea why there should be a connection?
Oh no, this is nobody had. Well, nobody has any idea. I mean, besides this comes some sort of crazy thing like, oh, because the zeta, this 0 is on one line, and there must be an operator behind this,
Okay.
and you know, and then this operator.
Oh, I see.
So
on line, it should be some kind of matrix, and then
yeah, and then it's a matrix. Then only matrix in the universe we know is this matrix. It's this kind of thing. But if you ask something more, then I mean, technically there are some similarity in various things one study, but I don't have any intuition why this is correct.
Well, what about Wigner's original intuition?
Oh, Wigner never. Oh, well, Wigner says it's highly correlated systems. So I don't really know for prime number, it's highly correlated. So that's a bit hard to say. But there's you know, there are active research, and people try to prove many different things about zeta function related to the random matrix, and there are truly many papers. But on the other hand, all these papers, the method are all pretty analytic number theory method, and it's not has not much to do with this. So they use the random matrix to guide their intuition. That's what's going on. Because they try to find some properties correct in random matrix and why it's correct, and then try to mimic the argument in the number theory setting. So that's what they are doing.
Thank you.
Thanks.
Okay, then thank you again for the talk.
Yeah, thanks.